Now that we know the life cycle of a FlexV state, we are ready to create our own state implementation. In this video, we will apply what we have learned to program a state that controls the conveyor belt in our factory simulation. Okay, the first thing we will do is not to open our code editor, but to think about the design of our state before programming anything. Remember the design principle for states that we discussed in the previous videos. Our state should use a robot capability that is implemented by a ROS node. That is, it should simply involve a client call. In our case, the capability is controlling the conveyor belt. And we are lucky. In the course repository, there is already a node that implements a service just for that. This service takes as a request parameter a float value with the power to apply in the conveyor, which causes it to move at a certain speed, and returns a Boolean indicating if setting that new speed was successful. So, we need to think how we are going to use this service in our state. What should happen when our state becomes active? Well, we want the conveyor belt to start moving at the given speed. And then, what outcomes can result from our state? In this case, our conveyor belt service simply returns a Boolean. So the potential outcomes are that we either succeeded or failed using the service to set up the speed. Additionally, we should think of how we are going to interact with this state from the state machine. Is there any runtime information we need to pass to the state? Which input keys should our state have? Well, the conveyor belt service has as input argument the power. So a priori, it seems reasonable to have this value as the input key to our state. We can rather call it speed with the same type, float. Okay, now the output keys. Do we expect any information returned by our state after its execution? Well, the only output of the service is whether it was successful or not. And we are already capturing this information in the outcome of the state. So we don't need an output key for that. Finally, do we need any parameters to configure this state for our specific applications? What if we want to stop the conveyor belt instead of setting a certain speed for it? We know that we can do that by setting the speed to 0. But probably it's more clear if there is an explicit parameter to define whether the state is used to set a certain speed for the conveyor belt or it stops it by setting the speed to 0. So we can define a Boolean parameter stop that could be set to true for the state activation to stop the conveyor belt, or false for the case of it setting it to a particular speed. Okay, now that we have the design of our state, we are ready to start coding our state implementation. So now we can open our text editor. Okay, first of all, FlexV state implementations are Python classes. We will call ours setConveyorPowerState to make it clear that it is a FlexV state. Following standard naming conventions in ROS, we will use lowercase with underscores for the file name, whereas for the class itself, we will use capitalized words. Our class will be executable and will connect to a ROS system. So we start our code with the same declaration and importing ROS.py as in all the code templates you have been using during this MOOC. Next, for our class to be a FlexV state that follows the life cycle discussed in the previous video, it needs to inherit from the event state class in FlexV. So we also need to import it from FlexV_core. Okay, now we can start implementing our state class. First of all, it is very important that we document our state. This is basically writing down our design for it. It is very important for two reasons. First, This way, other ROS users, including yourselves in a few weeks, can understand how to use the state. And secondly, the FlexB app parses the documentation that we put here in the code and displays it in its user interface. Okay, this is how the documentation looks for our example. Let's go through it. The documentation of a state is a Python docstring that follows the class declaration. First, it contains a description of the purpose of the state. After the description, the state interface is documented. That is, the state parameters, input and output keys, and outcomes that we have defined in our state design, with one line per element. Each line follows the same convention. First, the type of the element. In this case, 2 dashes mean that this is a parameter. Then, the name of the element, stop in this case, and its type, a Boolean. Finally, a description. In this case, the parameter stop is used to indicate if a particular instance of set conveyor belt powered state will stop the conveyor belt independently of the speed sent to it, or will do otherwise. The next element we have is an input key, as denoted by greater than and hash. We call it speed, and it is of type float. And we have here its description. Finally, the 2 possible outcomes of our state are defined with minor than and equal symbols, followed by the name, in this case succeeded and failed. Note that the outcomes do not have a type, but they do have a description. Okay, this completes the documentation of our state implementation. Now we can start coding our state functionality by implementing the different functions of the FlexB state lifecycle. We will start with the constructor, the init function. First of all, the init function takes as argument the parameters of our state. In this case, stop. Now we have to declare the outcomes and input and output keys of the state. We do so by calling the superconstructor with those arguments. In our case, the outcomes succeeded and failed, and the input key speed. Remember that the constructor is called when all states are initialized before execution of the behavior. Therefore, it is the place to initialize variables and connections to the ROS system. So we use it to store the value of the parameter stop for further use inside of our class, and to initialize our client for the conveyor service. This is done through a FlexB proxy. Okay, we will not enter into the details of FlexB proxies. You can read the documentation about them in the FlexB wiki. But let's say that they are a more efficient way to handle multiple ROS subscribers, publishers, and service and action clients. In our case, we want the state to use a client for the conveyor belt ROS service. So in our import section, we add the FlexB proxy for service calls. We also need to import the classes for the conveyor belt service and its request, which are in the HRWROS Gazebo package in the repository of the course. Okay, now coming back to our constructor, we initialize the service caller proxy by passing it a dictionary containing their service name and its type. To find the service topic name, we can use ROS service list and ROS service info in our system. Here you see the name for the conveyor belt service offered by the factory simulation. We store it in a variable so that we can use it later. Okay, we have finished the implementation of the constructor for our state. Let's implement now what happens when a behavior enters our state. Remember that this is the onEnter function that is called only once when the state becomes active. First of all, we need to collect the input keys to the state. This is why the user data is an argument to the onEnter function. So we collect the speed input key from user data in a class variable. Now, remember that the onEnter function is the main place to implement the functionality of a state. So we will make the service call here. Our service call depends on two things: the parameter stop and the input key speed. We have designed our state so that if the parameter stop is true, then the state will stop the conveyor belt by setting its power to 0, no matter what is in the speed. However, otherwise, we set the power as indicated by the speed input key. Finally, we make our service call to set the conveyor belt speed. We should make it catching any errors that may arise. So we put it within a try-catch block. And we reflect the occurrence of errors in a class variable _failed that we will use next to determine the outcome of our state. This outcome of a state is typically determined in the execute function. This function also takes the user data as an argument. Execute is called periodically at a default frequency of 10 Hz after the onEnter method, while the state is active, that is, only until it returns an outcome. The execute function is used to evaluate conditions to decide whether the state can return any of its outcomes. So in our case, we check if our request to set the conveyor power was successful. For this, we need to check two conditions. First, that there was no error trigger when sending the request. We have stored this in the failed variable. If errors were triggered, we set the outcome of our state to failed. If there were no errors sending our request, we still need to check the result of our service call. Only if it was successful, we set the outcome to succeeded. Otherwise, the outcome of our state is failed. Okay, looks like we have coded all we needed in our state, right? Well, actually not. We haven't implemented the onStart, onExit, and onStop functions in the life cycle. OnStart is triggered when the behavior is started. We could have used it to initialize our variables. However, it is better to do it as we did in the constructor, because if anything fails, the start function might not be called. So we don't need to do anything in our implementation of onStart. Next, onExit. Remember that this is the function called once an outcome is returned to stop any running processes initiated by the state. But in our case, the outcome is returned after resolving the service call, and there are no more processes we need to stop. So we don't need to do anything in this function either. Finally, the onStop method is called when the behavior stops, either because of finishing or because of being canceled. It is used to clean up things. Since we don't have anything to clean, we can leave this one empty too. Okay, now we have really coded all we needed in our state. In this video, we have learned how to create our own FlexV state implementation. In the following video, you can see the result. We will use the new state to extend our peak behavior by using the conveyor belt in the factory simulation.